Hey team, welcome to part 6, the last part of my first law of thermodynamics series. We are wrapping this up by doing a meteorology example thermodynamics problem. It's going to be very exciting. The problem that we're doing is problem 3.32 from the textbook Atmospheric Sciences by Walter and Hobbs. My mic cuts out when I say that in the actual video, so I thought I would say it here up front. Okay. Let's get into it. Okay, team, first things first, I'm gonna write the problem down. A quick note that the problem that we're doing is problem 3.32, Atmospheric Science by Wallace and Hobbs. This is a really great textbook. It's a textbook we used for the first class I took in meteorology grad school. And yeah, it's a good book. So there's my reference. What we're trying to do here is calculate how much work is done on a parcel of air that has a mass of 2 kilograms if we're going to isothermally compress that sucker to 1/10 of its original volume, and we're going to hold this at a constant temperature. So this question is a direct analog to the isothermal compression phase of our Carnot cycle that we just finished talking about. We don't need to reinvent the wheel here. We already know how to do this problem. What we're going to think about here is that the amount of work done is going to be related to that pressure times the change in volume. So I'm going to write that out like this. The work done divided by mass, because we've divided all of our terms by mass. So the work done divided by the mass of the system is equal to negative, because this is work done on a system, not work done by the system. And so in thermodynamics, we define work done on a system to be this negative value. So negative the integral of pressure with respect to that specific volume. If you're not familiar with the integral, again, no worries, we're just gonna end up with that natural log thing here in a second. So we're going to do our same substitution where we know that pressure equals the dry gas constant times temperature divided by specific volume. So let's plug that in here, and I'll divide this mass over. So I went ahead and just put in a 2 here for mass, because we're told that the mass of our parcel of dry air is 2 kilograms. We were given that in the problem. So I went ahead and just put that there. I went ahead and pulled my gas constant and my temperature out of the integral, because we know that those two things are constants in this system. A quick note that the gas constant for dry air, R, is going to equal, it's 287 joules per Kelvin. And this is a number that I Googled. You can just look this up. The other thing we're gonna do is convert our temperature from Celsius to Kelvin. So to convert from Celsius to Kelvin, you just add 273. So the temperature of my system in Kelvin is 288 degrees Kelvin, and we already know that the integral of d alpha over alpha is just the natural log of my final specific volume divided by my initial. So let's go ahead and write all of that out. Now I have to check framing. Then the last thing we need to do is relate alpha to my final volume to my initial volume, where we're already told that my final volume is going to be 1/10 my initial. So we can say this. Specific volume 2, 1/10 specific volume 1. We'll substitute that in. Now I've got alpha 1 over alpha 1, so that they cancel each other out to 1, and we're just gonna take the natural log of 1/10. Now I've got something I can plug into a calculator. And if I do that, what I will end up with is 3.806 times 10 to the 5th joules. I actually really like this problem because how many times in these videos have I said, now let's imagine a balloon and we're gonna raise our balloon up into the atmosphere and it's going to expand or it's going to compress when we bring it back down. That's a little thought experiment we use all the time, but now that we've learned some thermodynamics, just a little bit of the first law, we can start putting actual numbers to it so we can get a little more solid grounding, solid mathematical foundation for our understanding of just what is going on in the atmosphere. Okay, I think that's actually, is this the end? Is this the end of the thermo series? I don't know. Maybe, possibly. Okay, team, while that is certainly not all there is to say about the first law of thermodynamics, that's all I've got to say about it for this series. I hope you all liked these videos. I hope they were informational. Thank you so much for sticking it out all the way to the end. You're a superstar. And I will see you guys in the next video that will be on a different topic. I've been wearing this sweatshirt for days.